Good afternoon. My name is David Markham.
And I am James Beasley.
We're the poster children for the late life secondary career foray into the educational arena. We teach at Hamilton High School in Northwest Alabama, and we are responsible for all the physical science classes in grades 10 through 12, basically physics, chemistry, AP chemistry, environmental science, earth and space science, and physical science.
We want to give a special shout out to our mentor for this NASA adventure, to Mr. Jeff Robinson. Jeff is an aerospace engineer here at Langley Research Center. He is the technical lead for NASA's hypersonics project. I would like to say that Jeff has went overboard with us. He has been very, very helpful. We really didn't have a clue as to what we were going to do our project on, and he had researched various topics and let us pick.
Good afternoon. My name is David Markham.
And I am James Beasley.
We're the original poster children for the late life secondary career foray into educational adventures. We're privileged to teach at Hamilton High School in Northwest Alabama, and we are responsible for all of the physical science-based courses at our high school, namely physics, chemistry, AP chemistry, environmental science, earth and space science, and physical science in the 10th grade area.
We would like to give a special thank you to our mentor for this NASA project, Mr. Jeff Robinson. Jeff is an aerospace engineer here at Langley Research Center. He is the technical lead for NASA's hypersonics project. Jeff has graciously went overboard with us. He has researched topics for us. Coming into this experience, we really had no clue as to the topic that we would pick. Jeff threw out a handful of topics for us, and I think you're going to enjoy what we have coming up for you.
We envisioned this, obviously at NASA you think rocket science. We developed this curriculum for a 2-week session based on 50-minute lessons and designed as a cornerstone project on rocket-based propulsion. It would be the second in a series of 3 which would begin in the 10th grade in physical science and develop as a tie-in to the curriculum. The first of these being basic principles of flight that students would encounter in 10th grade physical science, which would naturally follow lessons of Newton's laws and fluids. The rocket-based propulsion would fit between these and would be followed by a third, also later on in our physics curriculum, focusing on gas turbine compressor-based propulsion methods as a natural tie-in to their curriculum, obviously after they've had instruction in fluids, gases, and some thermodynamics. All of these students would come equipped with a basic toolbox. They would all have had algebra, they would have trigonometry, geometry, and have experience with manipulating numbers in Excel spreadsheets.
And we envisioned day 1, the teacher would just go to the board and write the term rocket science. The old saying, hey, it's rocket science. We kind of fell onto that principle, and we would invite the students to tell us verbally what would come to mind when we said rocket science. You would get a sleuth of topics that came up: television, trajectory, space shuttle, going to the moon, blowing stuff up would be definitely one that came up. We would recommend writing all of these topics on the board, circling the ones that you're trying to get the point across to, basically just developing a concept map out of what the students are brainstorming at this point.
Next, we would work to engage them. Always give them a little historical background. It's very, very important in this case. They haven't had a lot of exposure to aerodynamics or rocketry-based propulsion methods. We have access to laptops. We would distribute laptops and let them use a little bit of a collaborative approach, group them in groups of 2 to 3. Draw a timeline on the board as an educator, assign specific period groupings to the students, and give them about 5 minutes to look for events within that time range, and thereby they gain a specific sense of hallmark events in the history of rocket-based propulsion.
We definitely need to cover the benefits of rocket technology, which is basically what comes to mind when the common person thinks of NASA. I stress to my students that the ultimate goal is to provide a better quality of life for not only themselves but their future families. So some of the benefits that come out of rocket technology, such as medical research, remote sensing of weather in Alabama where we're from, weather is one of the key aspects that we have to keep an eye on. Communications, you might ask your students, Sirius Radio, Dish Network, DirecTV, that kind of thing, all from the benefits of rocket technology, being able to put those satellites into space.
Next, we would want to continue this engagement with rocket-based propulsion, review the benefits, but really go back to the basis of all science, asking them the how and the why. How does it impact us? We're bridging here. We've talked about the history. We've talked about how it has been harnessed to provide a better quality of life. And, you know, we want to continue to advance this understanding, the key to true understanding, taking them from science and bridging all the way to engineering. Science, we tend to get tied up in the science and learning for sake of science sake, which is nice. It's important, but we need to learn and teach our students to become more functional and application-based and help them engage so that they'll be prepared for a real-world experience.
Day 2 would be simply a review. By this time, the students in these upper-level physics classes will definitely know Newton's 3 laws of motion. We want to tie those 3 familiar laws of motion into an aerospace perspective. We would have the students recite, starting with the first law, an object at rest remains at rest, object at motion tends to remain in motion, unless acted on by an external force. A rocket would be, here's an example. You could set a rocket on a table and say, you know, what forces are acting on this rocket at this time? And you would have forces going in all directions around it. You know, basically, an object at rest remains at rest. When the rocket blasts off, you would ask the student at that time, what kind of external forces are occurring now? And we would have a rocket that would blast off with the external forces, of course, being the propulsion.
Then you can naturally lead into Newton's second law of motion. And obviously they would recognize this if any of them have any background in Star Wars, and you can say that Newton apparently was a fan of Star Wars. But engage them and say, how many of you have ever seen the launch of a space shuttle? And of course, they are familiar with this. They've all seen it. And we would show a video at this time and ask them, what is the relative velocity of the shuttle versus the exhaust stream coming out of the nozzle? And emphasize that the shuttle has a very large mass with little velocity at the time of liftoff, but it is balanced by all of the combined small masses of the combustion products emanating from the nozzle, which gives the whole system an incredible acceleration. And we would obviously use this as a bridge to Newton's third law, which they're very familiar with. For every action, there's an equal and opposite reaction. And you can use something as simple as a balloon to emphasize that point. And my air is leaked out, so you get the idea. Always use little examples or little demos. Ask students to identify the action and reaction in that case. Now, at this point, with this review, you stress that they've had everything they need to know to be a rocket scientist. But what they need to actually do is to be able to apply these concepts. and we are starting to lead them into some of the future activities of designing a rocket, which keeps them excited about the topic. If they're going to build a rocket, what are some applications? They know that. But if they're going to build a functional rocket, how big does it need to be to complete the task? How far will it need to travel? Taking into account considerations such as size and payload. How much propellant are they going to need? How will it be steered? What materials will they construct it out of? So these basic things are things they need to know. We're leading them from a science standpoint to helping them become functional with this entire exercise. As part of what we would call a pre-assignment for the night, they would be given some homework to develop a conceptual framework for future assignments that they will be doing in the next few days. They will be giving diagrams to research. In this class, honors-based physics, they would have access to computers. We have them in the classroom. But they would be given things such as rocket-based propulsion terminology, solid-liquid propulsion types, basic reactions between fuel and oxidizer, advantages and disadvantages of the systems, generation of thrust, control of mass, directional control, just to get them a working knowledge. Go backwards there. And day 3, we're going to re-engage those students. We're going to take these pre-assessment questions, engage them with a PowerPoint-based lecture embedded with some problems. We're continuing to check for understanding as we talk. A great resource here would be the Space Math site at NASA. Lots of great questions, variable mathematic proficiency depending on what your students' proficiencies are. We're going to talk through the questions from the previous night, embed with some problems that they will learn how to work, and then have more hands-on experience. There's just some examples here. We've taught them about basic solid propulsion systems. We're giving them a question here to emphasize thrust curves, rate of propellant burn to thrust, and very simple problems here. Lots of those. Also embedded within this would be some little nuggets of history. If you are in any way familiar with rocket-based propulsion, you are familiar with Konstantin Tsiolkovsky, who was one of the first to envision the concept of space flight. And you're also familiar with what is known as the rocket equation, which lends itself to calculating the amount of fuel a rocket would need to break free from the gravitational field of the Earth, as well as figuring mass fraction calculations for a spacecraft, which our students will do. Just another example of an exercise. They're all familiar with graphing X and Y coordinates. We would ask them, give them an example of a configuration with the solid rocket booster. They would be to create a thrust file of thrust versus time, predict what the thrust profile would look like as the fuel burns outward from core to outer layer. Just basic things, and notice that we're getting them into the concept of thrust versus time, which we will continue to build upon as we progress.
And days 4 and 5, this would be a lab activity. We're going to call it rocket modeling and simulation. This brings in a lot of the simulation aspects that we have learned while we're here at NASA. This is actually the governor of California, Arnold Schwarzenegger. Everyone loves video games, and that's one of the things that you would like to ask your children, your students. Who likes video games? This would bring it into a topic where you could explain and let them comprehend that a video game is more than often a simulation of an occurrence, giving them a better understanding of why and how and why engineers use simulation and modeling. Going back to Mr. Jeff Robinson, one of the first things that we were excited about seeing his work facility, and he said, well, it's basically a desk with a few monitors on it. So we were, we were almost disappointed at first, but then we came back and we were excited to find out that basically his whole career has been through modeling and simulation. That's what we want to carry to the classroom. This is a simulation that we were that we were shown by Mr. Tom Benson. I think he was actually the developer of this. It's called Rocket Modeler 3. And I want to go back to that. Rocket Modeler 3, and let's get this center just right. What I would have the students do in this, this exercise, I would give them a sheet that had a specific rocket build that I have gone through and tested. They would put in, and I'll just kind of follow through this. You can put in your design, you can put in your fuel. Back on design, you can change down here, you can change the length, the diameter. You can actually change your fins. One thing you want to make sure that they do is change it to metric. And we want to change it to a solid rocket. These are solid rockets that we're talking about. Again, you can change your nose cone, you can change your payload. You can basically take almost any kind of rocket that the students might envision and simulate it through this NASA simulator. Change the fuel type. We can pick engines. Almost all of the rocket engines that we could find, even on the internet, are listed in this. Change your launch pad, which we will be shooting at a complete vertical angle, but if you wanted to do a projectile type simulation, you could do it from here. This will take care of anything you want it to do. You can change it from Earth to Mars. What I want them to do, what I want the children to do would be to take what the variables are that I give them, and by explaining it through an LCD projector, direct them through this stage, let them simulate building this rocket, put in all the variables, and then actually fly the rocket. With the simulator here, we'll go through real quick. We'll say go and then fuel, and you can actually go through and fly. There's a countdown. Fly your rocket, and it will tell you the estimated height and speed of the rocket that you've built. And then once they get that, I have them go back and do things. And I'll go back over to this other page here. This is the instructions. Go back and add a payload, add a 15.8 gram payload to the rocket. See what that does to the ceiling height. See what that does to the speed. Changing engines. Go to more powerful engines. See what that does to it. Add or increase your payload up to 100 grams. See what that does to it. And then finally go to the moon. See what the gravitational effect and the atmospheric conditions will do to that. Students will then design their own rocket and fly the rocket that they have designed 10 times by adding mass to the rocket in exact increments over the time flight of 10 different flights, and they will develop a chart. This is the red here that you can see by my cursor. That's the height. As you add mass, of course, the ceiling height will drop. As you add mass, of course, the velocity will drop as well.
Day 6 and 7 is measuring thrust and predicting trajectory for a model rocket. To this point, they've thoroughly embedded with Newton's laws. They've used the Rocket Simulator 3 to plug in numbers and see how the variables influence model rocket flight on a simulator. Now, numerical simulation, they will have developed this familiarity, obviously, with using the simulations. But if we think about it, when they are working traditional two-dimensional kinematics, we're using constant mass, constant velocity. What we want to engage them with now is to throw some other uncertainty into the mix. When we're dealing with rockets, as everyone's aware, we're not dealing with constant mass. Mass changes, velocity changes, different forces are in effect. We have drag forces. They've kind of envisioned that, but what we want to do now is engage them with numerical simulation using probeware. Probeware is very much encouraged. It's an easy way to collect and analyze data that you could not otherwise investigate. If you're wanting to find a true mathematical relationship among measured variables. And as all of us have this issue, short data collection time. And we can collect the data, we can take the data with us. And this data is very important to understanding the core semblance of what this exercise is all about. And what we are familiar with using, most of people are very familiar with either using Vernier or Pasco-based data collection systems, being a LabQuest if you're familiar with Vernier, or a GLX if you're dealing with Pasco. Both of them work equally. You can outfit them with a force sensor. Now, we were working diligently to try to make sure before we incorporated this lab that we could actually use this in the classroom. We had no easy access to supplies or ideas, but we thought we can use database collection methods with standard equipment that's available in most high schools. And so we physically went out and constructed a very high-tech data collection device that would hold a model rocket, which they are used to downloading data from. This is obviously not loaded. This incorporates, for $20, we have equipped this lab with your basic toilet flange from Lowe's, pieces of PVC pipe which act as a holder for the model rocket engine, attached to a force probe, which easily plugs into our Pasco GLX, and it makes a very handy collection device. And this is what you see on the screen. For about $20 and a little bit of time, you can easily construct this. And everyone, as you're well aware, as teachers, we have to be very inventive.
If you look on your screen now, this is an actual video that I taped of us firing one of the rocket engines back at the hotel.
Ready, aim, fire.
And it'll actually display a really good graph for you. It's a cool. We have a saying back in our school: if we think it's cool, they'll think it's cool. So it's a cool little experiment that you can do. You can basically compare manufacturer specs to what you get.
And as you're well aware, they are used to inputting the data for the specific engine. They've already had to do that with the Rocket Sim 3. What they don't realize, and once again going back to graphic interpretation of thrust over time, when they plug in numbers, they're getting the total thrust. But when we take, and we had used an Estes rocket model there, which was a published data curve. This is our data curve that we collected the other evening on the same rocket motor. And when they do this, they're able to see there can be a substantial difference between what is reported as manufacturer specs versus what they can actually obtain using their own data collection methods. And through this exercise, the various groups in the classroom will be able to actually model every rocket engine that they would be capable of using in the upcoming exercise. So they will have actual data. This is just a screenshot after the data has been transferred. You can get it in tabular form, you can graph it, you can calculate area under the curve to get total impulse. And then the logical extension of this activity, we've already used the concept of numerical modeling to help them understand that to solve a problem like this with changing variables, they have to break it down into very small increments, which we've done that with the probeware. We've had it to sample. You can set it to sample 50 or 100 times per second. You can download it to a spreadsheet. We would give them give them the equations. They would break it down and make their own spreadsheet. This one takes about 150 calculations to go through the thrust portion of the flight. And what they're doing, they're basically, after they download the thrust, they can calculate drag, net force, acceleration, velocity, y or altitude, and they can sum everything and get an impulse value that meshes or maybe doesn't mesh with what their values are for the spec. And so they've automatically got data here, except they're confronted now with which data do I actually use. They're in a real world situation here. And okay, go.
All right. Day 8, we would envision rocket engineering. We titled this "Let the Games Begin." This is kind of what a lot of the students have been waiting on. They've had 8 days of experiments, lab exercises, lecture, problem solving, that kind of thing. So now we are actually going to start engineering rockets. Rules of engagement. We're going to talk about the grading. They're going to be grading on results, design, originality, data. We're going to put a ceiling height for these rockets at 61 meters, or about 200 feet. Rewards will be given to the winners. Everyone will receive a certificate. And we have plenty of NASA goodies to go around. Basically what this does is ties everything that we've done in this unit, simulation, spreadsheets, data, manufacturer specs, everything that we've done back into a real life situation of firing model rockets. We're going to have deadlines on it. We're going to have different rocket kits where where they can actually go in and use originality to custom design their rockets. Speaking of kits, here's just an example of one of the kits that we picked up. This rocket kit, it's one of Estes. There's a lot of manufacturers out there that make model rockets, but this kit comes, I actually showed you here, it's $23.99 straight out the door. You can build 2 rocket kits with this. One thing that we do recommend is that you get a rocket with a payload design. If you'll switch back to me real quick, some of the rockets, this is a larger rocket, but the nose cone will actually separate where you can actually put a payload in them. We really do recommend that type of rocket over all the others, simply because of the ceiling height that we have basically set up in the rules. 200 feet or 61 meters is going to be a goal. They can't go over that ceiling height. So they're going to have to really use the simulation. They're going to have to use the spreadsheets. They're going to have to use everything that we've covered in order to meet that criteria. And by the way, they have one chance. They have one chance at the flight. It's make it or break it. When they start assembling the rocket, please, 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 teachers, make sure that you give them the parts template. The instructions that come with the rockets are easy to understand. They're great. It took us about 35 minutes to actually build a couple rockets. But it refers back to the parts as part K, part M, part L, whatever. Make sure that they lay everything out on the template. Here's a little rocket there's a nice shot of our hotel room that we've spent the last 2 weeks on. It's a model that it took 35 minutes to build 2 of these. So it's something that you can definitely do. We're used to a 50-minute class period, something that you can definitely do in that class period. Then the next thing they will do is take their rocket, and they will determine in the center of mass. Use a string balance. This is actually showing a water rocket, but you can do it with any kind of rocket. Basically, you just take a string, wrap it around it, find the balance point. We're going to call that CM, that's center of mass. And then the next thing you'll do is find your center of pressure. You can take and project a shadow, or you can actually take and trace the outside, basically the outline of your rocket onto a piece of cardboard, cut that out, balance that image or balance that representation on a ruler, and wherever it does balance, that's your center of pressure. This is just another example straight from the NASA's rocket guide to show you, where you need to have your center of mass, where you need to have your center of pressure to make the rocket fly. They'll have a specification sheet where they have to measure and they have to mass every component of their rocket. They'll have to figure ISP. They'll have to figure CM, CP, everything they need to do. And then we go back to the simulator. Once they have their finished rocket that they're going to have to add payload to, they'll have to go back and redesign it from their measurements, from their sheet. They will have to fly the rocket over and over in the test, use the spreadsheets, use everything that we've done in this lesson to get the best prediction they can over their one-shot challenge.
Day 9. This is what they've all been waiting on. Safety first. A lot of you may be a little apprehensive, or you have administrators that are a little bit apprehensive about utilizing model rocketry. Absolutely respect what you're dealing with, but don't fear it. The National Association of Model Rocketry has great guidelines for firing model rockets, as well as the manufacturers of these model rockets. The kids really look forward to this. It's a great experience for them. They've had a chance to design. The models that we use are easy to build and easy to launch. Some video here.
1, 2, 3. I see that one. Cool.
Where is it?
One of the reasons we limited the ceiling to about 200 feet, if you're using trigger-based inclinometers or a smartphone app, these rockets are fast. They go high, and it's difficult to track them at times. But either way, we want to utilize all the remaining students in data collection for the altitude using the typical right triangle trigonometric method, which we're all experienced with. And there's a cell phone app. I think are easy. Most of the kids, we want to engage them with 21st century technology, and these are available for smartphones, and it's an easy way to utilize it. Day 10. Final exercise. We like to engage these students with what we call topics in a hat. Previously, about 3 to 4 days before this, they'll randomly draw a topic which the teacher has predetermined, and for the topic, they're all space and rocket-based propulsion oriented. They should be told that they're assigned to write a paragraph and be prepared to lead the class discussion, and they should pay attention to history, applications and benefits from each one of these historic events. And one of the last things that we engaged them with on the second day with the pre-application homework was we asked them, are solid liquid based rockets the only way to go? And we can use this as a springboard to investigate evolving technologies which can be embedded in this discussion.
Mr. Robinson?
Hi, RJ. What can I help you with today?
We're working on a school assignment to figure out what transportation will look like in 100 years.
Wow, that's a tough assignment.
We learned all about identifying problems, creating solutions, building models, and testing and evaluating data, which is all part of the engineering method.
Sounds like you have a really good handle on the process.
Thanks. But we need to learn more about what you do when the test results don't turn out as you expected.
Well, I can certainly tell you about that. We've been working on a program for about 8 years called HyperX. Although it's been very successful, we have had test results that were not always favorable.
What's the HyperX program?
Well, it's a series of small experimental research aircraft. Each one's about the size of a small car, and it's designed to test a new type of propulsion system called a scramjet.
How does it work?
But for a scramjet to work, the engine and the vehicle it's attached to must already be flying at a pretty fast speed, around Mach 3.
Mach 3? That's 3 times faster than the speed of sound. We learned in the case of the barking dog that sound travels at 330 meters per second. Times 3? That's 990 meters per second. Now that's fast.
Yes, it is. The engine uses the speed of the aircraft and its special shape to compress the air. Once the air is compressed, fuel is mixed in and burned, much like in a car engine, but with a lot less moving parts. The fuel-air mixture is then expanded out the back of the engine, and it propels the vehicle forward.
What are the benefits of using a scramjet rather than a regular engine?
Well, if you use a scramjet on a spacecraft, you don't have to carry as much oxygen on board as you do with today's conventional rockets. This would allow the vehicle to be lighter, safer, and less expensive. You can carry more cargo and payload to space.
Could it be used on a regular aircraft?
Yes, if we can successfully demonstrate this technology, it could allow us to build a whole new generation of aircraft. We could take off from the United States and fly to Japan in 2 hours. Today that trip takes 14.
Now that's the plane of the future.
And while a scramjet is not necessarily rocket-based propulsion, once again we're using this as a springboard to introduce some evolving technologies, which you saw in the video. And of course, videos like this are great introductions to evolving technologies. What they're going to come up with, they're going to come up with all sorts of things that they didn't realize before. Nuclear-based propulsion, solar-based propulsion, ion-based propulsion, which is already being used.
And the final thing with our presentation here is we want to talk about the next steps, how we're going to disseminate the information that we've gained over the wonderful 2 weeks that we've had at NASA. One thing that we really want to talk about is the Alabama Science Teacher Association. David and I have already been invited to be a couple of the main speakers at the next state conference. where we will go and present this information to all the science teachers in the state of Alabama. We're very excited about that. Alabama also has a wonderful program through Auburn University called Alabama Science in Motion. We have a physics, a biology, and a chemistry mentor out of our region that it's basically a lab in a box. They will provide the vernier, they will provide the passcode, printers, computers, test equipment, labs that you can do with your students. They bring them to you, they pick them up. They are very, very excited about the information that we're going to bring back to them and developing labs through aerospace. Another thing we're going to do is we're going to put links onto the various websites. We have a huge Marion County Schools website that parents and students go in and log in and get their grades. They can look at links, valuable asset there for dissemination. And we're going to do a beta project this year that's going to involve Facebook. A lot of our children, a lot of our students in a rural environment, they don't have internet at home, if you can believe that. But they still have the capabilities through text messaging to get on Facebook. We're going to start putting assignments, we're going to put links, we're going to put things like that on Facebook where they can log in with their phones, read the assignments. Just another great way using modern technology to keep up with your students.
As an ending, we would certainly like to thank everyone involved. We'd like to certainly thank our mentor Jeff Robinson, and as well as all the other mentors that were available. Have not strictly worked with their own students, but we certainly appreciate all of the ideas and time that they've devoted, along with the other scientists and engineers. Certainly very thankful to NASA for hosting this opportunity. And last but not least, all of the RTI professionals, especially Karen Kelly, Olivia Rice. We thank you so much for what you've done for us.
Thank you.